Cynthia Dwork and Differential Privacy, a comprehensive overview. Introduction. Cynthia Dwork is a pioneering figure in computer science, particularly known for her groundbreaking work in differential privacy. In an era where data privacy is increasingly under scrutiny, Dwork's contributions have provided a robust framework for balancing the need for data analysis with the imperative of individual privacy protection. This report outlines the evolution of differential privacy, its mathematical foundations, key innovations, practical applications, and the ongoing challenges in the field. Background: the need for privacy in data analysis. The concept of privacy in data analysis has a long history, dating back to the seminal work of Dalenius in 1977. Dalenius proposed that no information about an individual should be learnable from a statistical database unless that information could be acquired without access to the database itself. However, this ideal proved to be practically impossible to achieve. The quest for a feasible privacy-preserving framework led to the development of differential privacy. Foundations of differential privacy. Differential privacy provides a mathematically rigorous definition of privacy that quantifies the risk to an individual's privacy when their data is included in a dataset. At its core, differential privacy ensures that the inclusion or exclusion of a single individual's data does not significantly affect the outcome of any analysis, thus providing a strong privacy guarantee. The essence of differential privacy lies in the addition of calibrated noise to the results of queries made on the dataset. This noise acts as a buffer, obscuring the identities of individuals while allowing for accurate statistical analysis. Dwork's foundational paper on differential privacy was published in 2006, marking a significant milestone in the field. Her work established core principles and techniques that have since become the cornerstone of privacy-preserving data analysis. Key contributions and innovations. Cynthia Dwork's contributions to differential privacy can be categorized into several key areas. 1. Mathematical rigor. Dwork's work introduced a clear mathematical framework to measure privacy risks. The formalization of differential privacy involved the use of metrics to quantify how much the output of a function changes when a single individual's data is altered. 2. Algorithmic techniques. Dwork has co-authored numerous papers that detail various algorithms designed to achieve differential privacy. These include mechanisms for query-release data mining and machine learning applications. One notable collaborative effort is the book The Algorithmic Foundations of Differential Privacy, co-authored with Aaron Roth. This work presents fundamental techniques for achieving differential privacy and discusses the interplay between computational efficiency and privacy guarantees. 3. Practical applications. Dwork's research extends beyond theoretical foundations to practical applications across various domains. The techniques derived from differential privacy have been employed in public databases, healthcare analytics, and social science research, among others. For a recognition of limitations, while Dwork has emphasized the strengths of differential privacy, she also acknowledges its limitations. She has pointed out that while differential privacy offers robust privacy guarantees, it cannot guarantee complete privacy in all contexts. The challenge remains to balance the utility of data with the need for individual confidentiality. Applications of differential privacy. Differential privacy has seen widespread adoption in various fields. Government and public sector. The U.S. Census Bureau has implemented differential privacy techniques to protect the confidentiality of census data while still providing useful demographic statistics. Health data. Researchers are increasingly adopting differential privacy for healthcare data analysis, enabling the extraction of insights from sensitive health records without compromising patient privacy. Machine learning. Differentially private algorithms are being developed to train machine learning models on sensitive data, ensuring that the models do not inadvertently reveal information about individuals. Corporate data analytics. Companies use differential privacy to analyze customer data while safeguarding user privacy, fostering trust in compliance with data protection regulations. Challenges and future directions. Despite the advancements in differential privacy, several challenges persist. 1. Complexity and efficiency. Many differentially private algorithms can be computationally intensive, which may pose challenges in large-scale data applications. Ongoing research aims to optimize these algorithms to enhance efficiency without compromising privacy. 2. Dynamic datasets. Most current differential privacy techniques are designed for static databases. Developing methods that can handle dynamic datasets, including those that change over time, remains an area of active research. 3. User acceptance. As differential privacy becomes more prevalent, ensuring that individuals understand and trust the privacy protections being implemented is crucial. For policy and regulation, the intersection of differential privacy with legal frameworks and data protection regulations presents opportunities and challenges. Policymakers need to adapt regulations to incorporate privacy-preserving technologies without stifling innovation. Conclusion. Cynthia Dwork's work on differential privacy has been instrumental in shaping the landscape of data privacy in the digital age. By providing a robust and mathematically grounded framework, Dwork has enabled researchers and practitioners to analyze data while respecting individual privacy rights. As the field continues to evolve, the principles of differential privacy will likely play a pivotal role in addressing the growing concerns related to data privacy and security. The ongoing exploration of its applications, limitations, and future challenges will further cement differential privacy as a cornerstone of ethical data analysis practices. Cynthia Dwork's contributions to the field of differential privacy bring forth several counterintuitive insights that challenge common assumptions about data privacy and usability. Here are some of the most notable points. 1. Impossibility of complete privacy. Dwork's work highlights a fundamental impossibility result regarding privacy in statistical databases, which counters the intuitive belief that perfect privacy can be achieved. The seminal work of Dalenius 1977 suggested that no information should be learnable about an individual from a database without access to that database. Dwork's findings demonstrate that this goal cannot be realized in practical scenarios, even for individuals not present in the database. This stark realization underscores the inherent limitations of traditional privacy definitions. 2. Privacy versus utility trade-off. Another counterintuitive aspect of differential privacy is the notion that increasing privacy can sometimes lead to improved utility. Typically, one might expect that adding noise, which is a key mechanism in differential privacy, would degrade the quality of data or analysis. However, Dwork's research illustrates that by carefully calibrating the noise based on the sensitivity of the data, it is possible to enhance the accuracy of data analysis while still preserving individual privacy. This suggests that privacy and utility are not always in opposition as previously thought. 3. Adversarial power. The algorithms developed within the framework of differential privacy are designed to maintain privacy even against adversaries with arbitrary computational power. This stands in contrast to the common assumption that privacy guarantees are only effective against weak adversaries. Dwork's insights emphasize that robust privacy protections can withstand significant threats which may not align with the prevailing belief that stronger adversaries necessitate weaker privacy guarantees. For rethinking computational goals, Dwork argues for a paradigm shift in how computational problems are approached in privacy-preserving data analysis. Instead of merely substituting traditional methods with differentially private counterparts, she posits that rethinking the computational goals can lead to more effective and efficient privacy-preserving algorithms. This perspective challenges the conventional wisdom that simply applying privacy measures to existing frameworks will suffice. 5. Limitations of differential privacy. While differential privacy offers strong privacy guarantees, Dwork acknowledges that there are still fundamental limitations inherent in any method that aims to protect privacy. This admission challenges the notion that differential privacy is a panacea for all privacy concerns. Rather, it presents a more nuanced view that recognizes the complexities and trade-offs involved in privacy-preserving data analysis. 6. Dynamic data contexts. In traditional models, differential privacy is often discussed in the context of a single static database. However, Dwork's work extends the framework to more dynamic scenarios such as distributed databases and data streams. This expansion reveals that privacy considerations are more complex in these contexts, which may not be immediately apparent to those familiar only with static models. 7. Creative applications. Dwork highlights that differential privacy can enable creative applications beyond simple query release tasks. This indicates that the utility of differential privacy extends far beyond its original intent, encouraging researchers and practitioners to explore innovative ways to leverage privacy-preserving techniques in diverse areas including machine learning and mechanism design. 8. Intuition about noise addition. One might intuitively believe that adding randomness to data would inherently obscure meaningful insights. However, Dwork's framework demonstrates that when noise is appropriately calibrated relative to the sensitivity of the data, it can still yield valuable insights while safeguarding individual privacy. This challenges the assumption that noise always leads to a loss of information. These counterintuitive points from Dwork's work on differential privacy reveal a complex landscape of privacy considerations, emphasizing the need for nuanced understanding and innovative approaches to data protection in the age of big data. Cynthia Dwork's pioneering work on differential privacy has fundamentally shaped the discourse around privacy in data analysis. While many may focus on the high-level implications of her research, several nuanced aspects are significant yet often overlooked. Here are some of the key elements that merit closer examination. 1. Impossibility results and their implications. One of the most profound contributions Dwork made early in her career was the impossibility result relating to Dalenius's privacy desideratum. This result demonstrates that one cannot achieve perfect privacy while also providing accurate information about a dataset. The realization that traditional notions of privacy were unattainable paved the way for the development of differential privacy as a practical framework. This foundational understanding is crucial because it establishes the boundaries of what can be achieved in privacy-preserving data analysis. Many practitioners may not fully appreciate how these impossibility results inform the design of privacy mechanisms, leading to misconceptions about what differential privacy can and cannot do. 2. Mathematical rigor. Differential privacy is underpinned by a rigorous mathematical framework that quantifies privacy guarantees. The epsilon-delta definition of differential privacy provides a clear metric for privacy loss. This level of mathematical precision is significant as it demystifies privacy guarantees for stakeholders in data analysis, allowing them to make informed decisions about the trade-offs between privacy and data utility. However, the technical details and the importance of this mathematical rigor are frequently glossed over in discussions geared towards a broader audience, risking oversimplification of the framework's capabilities. 3. Utility versus privacy trade-offs. A critical point often overlooked is the conceptual trade-off between privacy and utility. While differential privacy aims to protect individual privacy, it does so by introducing noise into the data, which can diminish the accuracy of results. Dwork's work emphasizes that by rethinking computation and privacy goals, one can often achieve better outcomes than by merely adding noise to traditional methods. This insight is vital for practitioners who must navigate the delicate balance between the two and strive for practical solutions that maximize both privacy and data utility. 4. Algorithmic innovations. The development of various algorithms for achieving differential privacy is a complex topic that deserves more attention. The book, The Algorithmic Foundations of Differential Privacy, details numerous techniques and their applicability to different contexts, including query release and machine learning. The nuances of how these algorithms operate, their computational complexities, and their suitability for various applications are often lost in high-level discussions. Understanding these aspects is crucial for researchers and practitioners who must implement differential privacy in real-world scenarios and address specific challenges related to data types and analysis objectives. 5. Limitations and contextual considerations. Dwork acknowledges the limitations of differential privacy, noting that while it offers a robust framework, it cannot guarantee complete privacy in every situation. The effectiveness of differential privacy can vary significantly based on the context and the data involved. This nuance is particularly important as organizations increasingly seek to adopt differential privacy without fully understanding its limitations, which could lead to overconfidence in the protection it provides. Practitioners must engage critically with these limitations to ensure responsible and effective deployment of privacy-preserving mechanisms. 6. Real-world applications and case studies. The practical applications of differential privacy in various domains such as healthcare, social sciences, and economics are often overshadowed by its theoretical constructs. Dwork's insights into how differential privacy can be applied in practice, such as in the context of the U.S. Census Bureau's data releases, highlight the framework's real-world relevance. Understanding these applications can inspire new research directions and innovations in privacy-preserving technologies, yet they are frequently underrepresented in discussions surrounding differential privacy. 7. Broader implications for data policy and ethics. Dwork's work on differential privacy also carries broader implications for data policy and ethical considerations in data science. As organizations become more aware of privacy issues, the principles of differential privacy can inform ethical guidelines and regulatory frameworks governing data use. However, these discussions often remain at the periphery of technical discourse. Engaging with the ethical dimensions of differential privacy can foster a more comprehensive understanding of its societal impacts, encouraging responsible data practices. In conclusion, while Cynthia Dwork's contributions to differential privacy are widely recognized, many important aspects of her work are often overlooked in discussions. By focusing on the foundational and possibility results, the mathematical rigor of the framework, the nuanced trade-offs between privacy and utility, the algorithmic innovations, the limitations of differential privacy, real-world applications, and its implications for data policy and ethics, we can cultivate a deeper understanding of this critical area in computer science and its relevance to contemporary data challenges. Recognizing these nuances is essential for practitioners, researchers, and policymakers who aim to navigate the complexities of privacy in an increasingly data-driven world. 1. Mathematical framework and rigor of differential privacy. Cynthia Dwork's introduction of differential privacy marks a significant advancement in how privacy is conceptualized and measured in the realm of data analysis. The mathematical rigor underpinning this framework serves as a foundation for quantifying privacy risks, allowing researchers and practitioners to evaluate the trade-offs between data utility and individual privacy. This point invites an in-depth analysis of the mathematical principles of differential privacy, including its definitions, the role of noise addition, and the implications of privacy parameters like epsilon. A thorough examination can elucidate how these principles can be applied in various scenarios, highlighting the strengths and weaknesses of the differential privacy model compared to other privacy-preserving methods. 2. Algorithmic innovations and practical applications. Dwork's work emphasizes not only the theoretical aspects of differential privacy but also its algorithmic innovations and real-world applications. The transition from theory to practice is crucial as it demonstrates how differential privacy can be implemented in diverse fields such as healthcare, finance, and social sciences. An analysis of specific algorithms designed to achieve differential privacy, such as the Laplace mechanism and the Gaussian mechanism, can reveal insights into their effectiveness and computational complexity. Furthermore, exploring case studies where differential privacy has been successfully implemented allows for a discussion of best practices and lessons learned, as well as the challenges faced in deploying these algorithms in real-world settings. 3. Limitations and challenges of differential privacy. While differential privacy offers robust privacy guarantees, it is essential to recognize its limitations. Dwork acknowledges that achieving complete privacy in all contexts remains a challenge, and this opens the door for a critical discussion on the inherent trade-offs involved. Areas for exploration include the balance between privacy and data utility, the impact of varying levels of epsilon on the results, and the context-specific nature of privacy concerns. Moreover, examining scenarios where differential privacy may not suffice, such as in the presence of auxiliary information or when addressing specific demographic vulnerabilities, allows for a comprehensive understanding of the framework's boundaries. 4. Evolution and future of differential privacy. The historical timeline of differential privacy, from Dalenius' initial privacy desideratum to Dwork's foundational papers and the publication of the algorithmic foundations of differential privacy, illustrates the evolution of this field. An in-depth discussion could focus on how differential privacy has adapted to address emerging challenges in the digital age, such as the rise of big data and machine learning. Future directions for research and development, including advancements in real-time data privacy, differential privacy in distributed systems, and the implications of evolving regulatory landscapes, present opportunities for ongoing exploration. This point not only contextualizes Dwork's contributions but also encourages a forward-looking perspective on how differential privacy can continue to shape the future of data analysis and privacy protection. Here are 3 famous historical cases that relate to the themes of privacy, data protection, and ethical considerations in data usage. Similar to the work of Cynthia Dwork on differential privacy. 1. The U.S. Census Data Controversy. 2010 Census. The U.S. Census Bureau faces continuous scrutiny over how it collects and protects individual data. The 2010 census highlighted significant public concern regarding the confidentiality of personal information, particularly in the aftermath of increasing data breaches and privacy violations. In the lead-up to the census, advocacy groups raised alarms about the potential misuse of personal data by government agencies. The Census Bureau assured the public that it would maintain strict confidentiality and implement measures to protect individual responses. This incident underscores the tension between the need for accurate demographic data for policymaking and the imperative to safeguard personal privacy. It also reflects ongoing debates about what constitutes adequate privacy protections in large-scale data collection efforts. 2. The Cambridge Analytica Scandal. 2016. The Cambridge Analytica case is perhaps one of the most notorious examples of data misuse in recent history. This political consulting firm harvested personal data from millions of Facebook users without their consent, leveraging it to create targeted political advertising during the 2016 U.S. presidential election and the Brexit referendum. The scandal ignited global outrage and led to discussions about the ethical implications of data privacy, the responsibilities of tech companies in protecting user data, and the potential for manipulation in democratic processes. This case demonstrated the vulnerabilities of personal data in the digital age and emphasized the need for robust privacy frameworks echoing the principles of differential privacy that seek to protect individuals while enabling data analysis. 3. The Health Insurance Portability and Accountability Act. HIPAA. 1996. Enacted in the United States, HIPAA established national standards for the protection of health information. The law was a response to growing concerns about the confidentiality of patient records and the potential for misuse of sensitive health data. HIPAA introduced guidelines to ensure that individuals' medical information is handled securely and disclosed only with proper consent. Despite its implementation, breaches of patient privacy still occur, leading to ongoing debates about the adequacy of the protections in place. Particularly with the advent of digital health records and data analytics in healthcare. HIPAA's focus on patient privacy and the ethical handling of health data parallels the aims of differential privacy in protecting individual identities while allowing for meaningful analysis of healthcare trends. These cases illustrate the complex interplay between privacy data collection and ethical considerations, highlighting the ongoing need for effective privacy-preserving measures like differential privacy. Future outlook on differential privacy and its implications. The concept of differential privacy as developed by Cynthia Dwork and her collaborators has revolutionized the way we think about data privacy. As we look to the future, several key predictions can be made regarding the evolution of differential privacy, its applications, challenges, and the broader implications for society. 1. Widespread adoption in data governance. As regulations around data privacy become increasingly stringent, exemplified by laws like GDPR in Europe and CCPA in California, organizations will increasingly adopt differential privacy as a standard practice for data governance. In the coming years, it is likely that differential privacy will become a mandatory requirement for organizations that handle sensitive personal information. Companies will invest in developing differential privacy mechanisms to ensure compliance, thereby fostering a culture of privacy by design. 2. Advancements in algorithmic techniques. The field of differential privacy is still evolving, and we can anticipate significant advancements in algorithmic techniques. Researchers will continue to refine existing algorithms, making them more efficient and applicable to a broader range of data types and structures. Innovations in machine learning and artificial intelligence will lead to the development of new differential privacy algorithms that maintain accuracy while providing stronger privacy guarantees. The integration of differential privacy with advanced techniques like federated learning may also emerge, allowing for privacy-preserving models trained on decentralized data. 3. Interdisciplinary collaborations. The future of differential privacy will likely see increased collaboration across disciplines, including computer science, statistics, law, and ethics. As the implications of differential privacy stretch beyond technical boundaries, interdisciplinary teams will work together to address legal and ethical challenges related to data privacy. This collaboration will facilitate the creation of best practices, guidelines, and frameworks that ensure responsible implementation of differential privacy in various sectors, including healthcare, finance, and public services. 4. Enhanced tools and platforms. With the rising demand for data privacy solutions, we can expect the development of enhanced tools and platforms that simplify the implementation of differential privacy. These tools will enable organizations, including those without extensive technical expertise, to easily adopt differential privacy. Open-source libraries and frameworks will likely emerge, providing developers with ready-to-use solutions that can be integrated into existing systems. 5. Focus on usability and user education. As differential privacy becomes more widely adopted, there will be a growing emphasis on usability and user education. Organizations will need to communicate the benefits and limitations of differential privacy to both internal stakeholders and external users. Educational initiatives will aim to demystify differential privacy, enabling users to understand how their data is protected and fostering trust in data-driven applications. 6. Addressing limitations and challenges. While differential privacy offers strong privacy guarantees, it is not without limitations. Future research will focus on addressing these challenges, such as balancing privacy with data utility. For instance, the trade-off between the amount of noise added to ensure privacy and the fidelity of the data output will remain a critical area of exploration. Researchers will seek innovative solutions to minimize the impact of noise on data quality while still adhering to privacy standards. 7. Impact on social norms and behavior. As society becomes more aware of privacy concerns, the adoption of differential privacy could influence social norms and behaviors regarding data sharing. Individuals may become more selective about the data they share, favoring platforms that prioritize privacy. This shift could lead to a demand for transparency in how organizations handle data and implement privacy measures. As a result, businesses may need to rethink their data practices to remain competitive in a privacy-conscious market. 8. Global perspectives and variability in implementation. Differential privacy will not be applied uniformly across the globe. Different cultural attitudes toward privacy and varying regulatory environments will lead to diverse implementations of differential privacy. Countries with stringent privacy laws may adopt differential privacy more aggressively while others may lag behind. This variability will create a patchwork of privacy standards that organizations must navigate, potentially complicating international data sharing agreements. 9. Integration with emerging technologies. The future of differential privacy will also intersect with emerging technologies such as blockchain, Internet of Things, IoT, and edge computing. The integration of differential privacy with these technologies could enhance data security and privacy in decentralized systems. For example, differential privacy could be applied to data collected from IoT devices to protect individual privacy while enabling meaningful analysis of the data at scale. 10. Ethical considerations in public discourse. Lastly, the discourse surrounding differential privacy will expand to include ethical considerations. As the technology matures, discussions around the ethical implications of data collection, usage, and privacy will gain prominence. Stakeholders, including technologists, ethicists, and policymakers, will engage in meaningful dialogue to shape the ethical frameworks guiding the use of differential privacy in society. Conclusion. The future of differential privacy is poised for significant growth and development driven by technological advancements, regulatory pressures, and societal demands for privacy protection. Cynthia Dwork's foundational work will continue to inspire innovations and discussions around privacy-preserving data analysis, shaping a future where individuals can engage with data-driven technologies without compromising their privacy. As we navigate this evolving landscape, the balance between data utility and individual privacy will remain a critical challenge requiring ongoing collaboration and innovation.